get the new computer, it stops doing this thing that it's doing right now. I think it's interesting that we are talking about linear equations. So it sounds like we're talking about algebra 1, but we're not. Just a note from last time. That from our Wronskian criteria for linearly independent solutions to a homogeneous linear differential equation, if we have these solutions y1, y2, y3 to y sub n, our solutions to an nth order linear homogeneous differential equation, then the Wronskian of these functions are y1, y2, y sub n is either identically 0 that means 0 no matter what x is. That's what identically 0 means. And this would be for the trivial solution. Or it is never 0 on the interval of solution. So if the Wronskian y2 to y sub n is not equal to 0 for some x0 in the interval of solution, then our solutions are linearly independent. If you find one value of x where the Wronskian is not 0, that tells you those solutions are linearly independent. Because our Wronskian is either identically 0 or never 0. So if you find one value where it equals 0, sorry, where it doesn't equal 0, that tells you that you have your solutions are linearly independent. So I just wanted to circle back on that. So sometimes it is easier to pick a value of x like we did yesterday when we were doing a Wronskian than to actually do the determinant and simplify the algebra and do all that other stuff. So you can pick a value of x that seems like it would work. That is good enough. All right, a definition. We're going to define a fundamental set of solutions. Any set y1, y2, y3, up to y sub n, of n linearly independent solutions of an nth order homogeneous linear differential equation on some interval we call that any set. If we can find n linearly independent solutions, we call that a fundamental set of solutions. So we have an nth order linear homogeneous differential equation. If we can find n solutions, we call that a fundamental set of solutions. And we'll follow that up with a theorem. And our theorem says a fundamental set of solutions to the differential equation exists. And again, we're assuming that our differential equation satisfies the conditions for the existence of a solution. So this is a big revelation here. So we're assuming all the coefficients are continuous and not zero for all x in our interval of solution. Well, if that's true, then a fundamental set of solutions exists. We can find n linearly independent solutions to an nth order differential equation. Or not we can find, they exist. For most of what we do, we'll be able to find them, but the theorem just tells us those solutions exist. So finally, we are at the point where we can talk about a general solution. And this is a theorem about our general solution. Our theorem says if we have a fundamental set of solutions, then we have the general solution. So we're going to let y1, y2, up to yn be a fundamental set of solutions. The general solution and we're talking about the solution. I don't want to rewrite this nth order homogeneous linear differential equation again every time. So that's what we're talking about, the solution to that nth order homogeneous linear differential equation. The general solution is y equals c1 y1 of x plus c2 y2 of x plus dot 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 plus c sub n y sub n of x. Some arbitrary constants times each of our members of our set of fundamental solutions. So with nth order linear differential equations, homogeneous linear differential equations, our goal is to find n linearly independent solutions. Yes.
The fundamental set of solutions are linearly independent, then how can you add them together to get the general solution? Is that
Superposition.
they're dependent?
No, so if they're linearly independent, the only way that this adds up to be 0 is if this particular thing adds up to be 0 is if our constants are 0. So we're just saying we're adding all the solutions together. We're using the superposition principle here to add all the solutions together to get another solution to the differential equation. This one with n linearly independent functions, solutions, n linearly independent solutions, that gives us the general solution. And let's really quickly look at why this is the case. And I want to look at a second order example. So we're going to let capital Y, and I'm denoting capital Y with these bars, Y of t equal C1 Y1 of t plus C2 Y2 of t. And we're going to let that be a general solution. And this is a solution to a second order linear homogeneous differential equation. And we're going to assume y, capital Y of t equals k1 and capital Y prime of t equals k2 for some t. So we can think of this as our initial conditions. So if that is the case, we have, since y is this thing, we have C1 Y1 of t plus C2 Y2 of t equal k1. And C1 Y prime 1 of t plus C2 Y2 prime of t equals k2. Because this is our solution, this is what this implies. This system of equations, we have two equations. Our variables are C1 and C2. This system of equations has a solution unique C1, C2 if, and we're going to talk about something we talked about in pre-calc when we were solving systems of equations, if we turn this into a matrix system of equations. Matrix A times our variables equals matrix B. And we want to solve that using the inverse matrix. A inverse times B gives us our solution. We can find an inverse matrix if the determinant y1 of t, y2 of t, y prime 1 of t, y prime 2 of t, if that determinant is not 0. Well, what is this determinant? That's the Wronskian. So that's saying these things are linearly independent, the solutions are linearly independent, the Wronskian is not 0. We can find, if the Wronskian is not 0, this is not 0, we can find a unique C1 and C2 solving that system of equations. And if we expand and do a higher order differential equation, third, fourth, fifth, whatever, we get the same thing. If the determinant of this system is not 0, we can find a unique solution. So that condition that our solutions, our functions are linearly independent guarantees us we can find a solution to the system of equations that is given by our differential equation and our initial conditions. So we're back to linear algebra, systems of equations telling us we can find the solution, general solution to this differential equation. All right, so I think it's kind of nice because this connects back to stuff we've talked about in the past. It's not secret and magical. It's kind of back to tedious linear algebra. All right, so there we go. So let's look at an example. We're actually going to do some calculation here. So we have 4y double prime minus 4y prime plus y equals 0. And y1 equals e to the x over 2. And y2 equals x e to the x over 2. And we want to verify that these form a fundamental set of solutions. So we need to verify that they are solutions. Now we could use the superposition principle and add them together and take derivatives. I did it one at a time. I said for y1 prime is 1/2 e to the x over 2. y1 double prime is 1/4 e to the x over 2. And then I substitute that into the differential equation. 4 times 1/4 e to the x over 2 minus 4 times y prime, 1/2 e to the x over 2 plus y, 1, which is e to the x over 2, equals, and we add all this up and we get 0. So that is a solution. For y2, this is where we end with product rule. You end up with doing a lot of derivatives. This one's not terrible. y2 prime is x over 2 e to the x over 2 plus e to the x over 2. y2 double prime is x over 4 e to the x over 2 plus e to the x over 2. I combined some steps here. And then we substitute that into the differential equation. And I'm just going to write it this way. 4 y2 double prime minus 4 y2 prime plus y2. That does, in fact, if we do this algebra, we do get 0. You have to take my word for that. But I was very careful, and it did come out to be 0. So we have two solutions to a second order differential equation. What else do we need to make sure of here? We need to make sure they're linearly independent. So we're going to look at the Wronskian. So we're going to take the determinant, e to the x over 2, x e to the x over 2, 1/2 e to the x over 2, and x over 2 e to the x over 2, is that right? X over 4, right? Wait, let me look. Oh, this is y prime here. E to the x over 2 plus e to the x over 2. I was looking at y double prime. We'll form that determinant. And when you do this, you end up with after a little simplification, I'm going to distribute here and multiply here. We get x over 2 e to the x plus e to the x minus x over 2 e to the x equals e to the x, which is not 0 on negative infinity to infinity. So the Wronskian is not 0. So those solutions are linearly independent. And our general solution is y equals c1 e to the x over 2 plus c2x e to the x over 2. And we'll see tomorrow why we get this combination of e to the x over 2 and x e to the x over 2 as solutions here. And then we'll see on sort of block day, we'll see that. And on Friday, we'll see why those come up. All right, questions there? All right, let's talk about, finally, nonhomogeneous equations. And again, the non-homogeneous, homogeneous equations that we're talking about now are not the same as the equations that had homogeneous functions, where we'd use the substitution x equals tv or y equals ux. We're talking about we're using homogeneous in a different context. And I just want to say, recall a particular solution we found particular solution for first order differential equations by substituting in our initial conditions. A particular solution, y sub p, is free from arbitrary parameters. So we don't have arbitrary constants in particular solutions. So a theorem. We're going to let y sub p be any particular solution to the non-homogeneous differential equation. Linear differential equation. And not by non-homogeneous, I'm going to say linear nth order, and I'll leave out the nth order. Non-homogeneous, we have a sub n of x, y, n plus a sub n minus 1, x, the n minus first derivative, plus dot dot dot, plus a sub 1 of x, y prime, plus a sub 0 of x, y, equals g of x. This g of x here on the right-hand side is what makes this equation non-homogeneous. A homogeneous equation equals 0. So this is a, y sub p is a particular solution for this non-homogeneous equation on an interval. And let y1, y2, up to yn be a fundamental set of solutions for the associated homogeneous differential equation. And by homogeneous, we mean it equals 0 rather than g of x. The general solution to the non-homogeneous equation is y equals C1 y1 plus C2 y2 plus dot 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 plus Cn y sub n plus y sub p. Where the c's are arbitrary constants. So we have to include, when we solve a non-homogeneous differential equation, we have to include this solution to the associated homogeneous equation. Why is that? Well, if we take all these derivatives, nth derivative, n minus 1 derivative, this is the solution to the homogeneous equation. So if we take all these derivatives and add all of those together, this becomes 0 because it's the solution to the homogeneous equation. So it satisfies this differential equation equals 0. So we take all those derivatives for this part of the solution, we get 0. And then we have the derivatives of this, which we say then gives us g of x. So we have 0 plus g of x as our solution. So by the superposition principle, we have to include this because we can and add this, because when we take all the derivatives of this, multiply by the constants, and add them all up, this portion gives us 0. Yes?
Does that mean that you always have to do the non-homogeneous position value problems? Or
Yes. So when we start solving non-homogeneous differential equations, first we have to solve the homogeneous differential equation. Then we solve the non-homogeneous. And then we add those solutions together. We say, or we write, y equals y sub c plus y sub p, where y sub c is the complementary function. Which is the solution to the homogeneous differential equation. So solving a non-homogeneous differential equation always involves solving a homogeneous differential equation first. All right, so let's look at an example here. 2x squared y double prime plus 5x y prime plus y equals x squared minus x. Non-homogeneous, second order, linear differential equation. These are all functions of x. And I'm going to say y equals c1 x to the minus 1/2 plus c2 x to the minus 1 plus 1/15 x squared minus 1/6 x. We want to verify that y is a solution, a general solution on 0 to infinity. Can we agree that those functions are linearly independent? Hopefully it's relatively easy to see that. We can't multiply any of those by constants and add them together and get any of the others. All right. And this equation, we won't learn how, not in this class, we won't learn how to solve this particular kind of equation. This differential equation is called a Cauchy-Euler equation. And it's not difficult to solve, but there are quite a few steps. So we just need to take a couple derivatives here. Y prime equals, what did I get? Negative c1 over 2 x to the minus 3/2 minus c2 x to the minus 2 plus 2/15 x minus 1/6. Y double prime. I get 3 c1 over 4 x to the minus 5/2 plus 2c2 x to the minus 3 plus 2/15. And now we need to see that 2x squared times y double prime plus 5x y prime plus y, so plus this. That does, in fact, you have to trust me here. I have, here's my work on the page here, where I add this all multiplied by the x squared, the 2x squared, and the 5x, and combine like terms and all that stuff. That does, in fact, equal x squared minus 2, or sorry, x squared minus x. And in this case, we would say y sub c is c1 x to the minus 1/2 plus c2 x to the minus 1. That would be the solution to 2x squared y double prime plus 5x y prime plus y equals 0. And the particular solution, y sub p, is 1/15 x squared minus 1/6 x. And it will not be very long before we, well, not for this equation, where we talk about this and how we find these particular solutions. All right, finally, we're almost at the end here of our theory. The superposition principle for non-homogeneous equations. And we've kind of used the superposition principle here. The superposition principle. The superposition principle in general for differential equations tells us if we have a bunch of solutions to a differential equation, if we add them together, that is also a solution to the differential equation. That's the superposition principle in a nutshell. So let y sub p 1, y sub p 2, up to y sub p n. Those are k particular solutions to the non-homogeneous differential equation. So this is nth order linear non-homogeneous differential equation. On an interval, and this corresponds to, or the solutions correspond to distinct functions g1, g2, up to g sub n. So we have a non-homogeneous differential equation equals g1, another one equals g2, another one equals g sub n. These are the particular solutions for the one that equals g1, the one that equals g2. It's the same differential equation, but equaling different constants. Then y sub p equals yp1 plus y sub p2 plus dot 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 plus y sub pn is a particular solution to a sub n y to the yn derivative plus a sub n minus 1 and minus first derivative plus dot 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 plus a0y equals g1 plus g2 plus dot 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 plus gn. Sorry, gk. This should be a k. So we can find particular solutions individually, or we can consider this as one big function of x. We just add up all the particular solutions to get the particular solution to this thing. All right, so we're finally to the place where tomorrow, block day, we won't actually solve the differential equations. We'll be given a solution, but we'll find we'll find another solution. So given a solution, we find another solution. Friday, we will finally start solving higher order differential equations. I just wanted to kind of give some, I guess maybe a little bit of interpretation to what these equations might represent. If our differential equation a sub n of t, nth derivative plus a sub n minus 1 of t, and we're using time as our variable here. And this equals some g of t. This is modeling some situation. So we have an nth order linear non-homogeneous differential equation modeling some situation. We call y sub n, or sorry, the nth derivative of t, the n minus first derivative of t, those are called the state variables. They describe the state of the system at some particular time. What is the first derivative? What is the second derivative? What is the slope? What is the concavity? What is the position? What is the velocity? What is the acceleration? Etc. So those things describe the state of the system. G of t we call the input function. Or driving function. So we'll talk about a spring system. So you have a weight on a spring that's oscillating. Well, the input function might be you're pushing, giving a push to the weight on the spring, or you have a crank that's turning around and doing something. You have something heated, and you have some external heat source that varies in time. The heat goes up, the thermostat goes off, the heat goes back down. The temperature gets to a certain position, the thermostat comes back on, the heat goes back up. So your driving function might be the thermostat, and your input function might be some kind of periodic function of time. A solution is called the output or the response. So we get a solution, we call that the response to the driving function. And in the situation that we've been talking about, where we have a nth order linear non-homogeneous differential equation, the output is going to be uniquely determined. The functions, the coefficients, and our driving function uniquely determine the solution. So if you see this terminology, the state, driving function, response, etc., then you'll have an idea of what we're talking about. And we'll talk at the end of the chapter about a couple of specific kinds of driving functions for a certain physical situation, the weight on a spring, and talk about the response given various situations. The lesson next time is very short, and we have a block day. I would encourage you to plan on taking advantage of that time during block day to work on some of these homework problems. I find the stuff that we do on this homework, it's kind of tedious. You're taking a bunch of derivatives, you're adding stuff together, you're doing a determinant. What I'm doing is I'm making sign errors and I'm getting the wrong answer, and then I'm trying to figure out where I made a mistake. But it's just computational. It's very computational. It's not. That's kind of the nature of what we're doing here. When you verify, when you're doing the Wronskian, those kinds of things, it tends to be fairly tedious work. Give me just a second. Where is that? There we go.